So our introduction to analysis of variance. You should have seen this in your prerequisite course so that we're all on the same page with notation. Extending what we did in 5013 for two populations where we were just comparing two means equal to each other, we write, are there T different groups that have the same population mean? Okay? And all it takes for that null hypothesis to be false is at least one of them to be different. If we replaced all those equal signs with not equal signs, don't do that. Mathematically, that just doesn't make sense. Okay, so it just takes only one of them to be different to make the null hypothesis false. They could all be different, but that falls into the category of at least one. So, for an illustration, let's let T be equal to 4. We could look at all the pairwise comparisons using the independent t-test if we didn't know anything about analysis of variance. Just do all the possible t-tests. Well, that would mean I'd be doing 6 t-tests, just choosing things 2 at a time. Okay? The problem is that what we think we're doing with this type 1 error rate isn't being preserved. Because across all these 6 tests, we set each one of them with a type 1 error rate of alpha. Our actual type 1 error rate, then we'd have at least one type 1 error in, say, 6 tests. We would end up with 1 minus the probability of no type 1 error. So that would be, it's actually here less than or equal to 1 minus the probability of no type 1 error is what? Well, if alpha is 0.05 for probability of a type 1 error, the probability of no type 1 error is 1 minus 0.05 or 0.95 for all 6 of those tests. And when we compute this, what I have is 1 minus 0.7351, and that's 0.2649. So I thought I was doing tests at the 0.05, and I did for each possible pair, but when I look across the collection of these tests, I don't have a 0.05 test anymore. Would you ever think about doing a test at the 0.26 level? No. Okay, so one of the reasons that we're looking at analysis of variance is so we can control this type 1 error rate, because I don't want to declare a difference if it's not there. So we need a method that controls this type 1 error rate, evaluates this equal means assumption, and that method is referred to as analysis of variance. There are 2 common acronyms, ANOVA being one and the other is AOV. So our notation. We've already written before, as T is the number of levels of a treatment or a factor. N with subscript I is the sample size for treatment level I. And that if we sum the values of these NIs, where I ranges from 1 up to T, and if we add across an index, that index is replaced by a period. This is read as N dot. And so N dot is our grand sample size. Okay, so that if we have these T different levels, our different sample sizes, then we have N1, N2, up through N sub T. So it's the addition of all those NIs that give us our grand sample size. Our value here, Yij, this is the observation on the jth experimental unit in treatment level I. And which treatment group or population sample group is I, and then which observation. So what we have then, suppose we have a group 1, a group 2, and group 3. And if we measure our data, then we have a value here, then it would be Y observation 1, treatment level 1, observation 1. Treatment level 1, observation 2. Y2, observation 1. Y in group 2, observation 2, Y in group 2, observation 3. And we can keep going with these. So the first index here identifies from which treatment group or sample it comes from. Pardon me, it should be 3, 3. Okay, so here I just did them with unequal sample sizes. They could have all the same sample size. Okay, so that's what you know what the notation is. And so on the Yij's, you may see uppercase or lowercase in my notes in the book, and we mean the same thing. Okay, because I see I wrote capital YIJ down here. If we take this yi dot bar, what this is doing is it's for a fixed value of I, it's adding these guys up. So if you add these things up, you get y1 dot bar. If you add these things up this direction, pardon me, you get y2 dot. Whenever you divide by the sample size, you get the bar. So I said the bar before. So this is just the total of these guys, y21 plus y22 plus y23. Y2 dot bar would take that total and divide it by the sample size for N2. Okay? Again, the dot says which index has been summed over. So if we see the y dot dot, such as this is the grand total. So this says, first for set I equal 1, add up everything in all those in the first column. And I goes to 2, j resets to 1, and so that it would add up everything here. Okay, so it says across all I values from 1 to t, and within each value of I, the second index goes from 1 to the NI sample size. If we take that grand total and divide by the grand sample size, we get the grand mean for the experiment. Additionally, for each one of these samples, we can compute a standard deviation or variance, and so S sub I squared is the sample variance for each of those groups. This is how we identify those. Okay? So sample variance, we could write S sub I squared. How do we compute that? Do you recall? So I stays fixed, so it just means I'm adding a cup across the j equals 1 to NI. It's how much does each observation in that group deviate about the sample mean for that group. We square those, and that was divided by sample size minus 1. Does that look familiar? And we define this term called total variation or total sum of squares. We are taking items in parentheses here, could be positive or negative, and we're squaring them. Okay, and if we add up squared items, those are referred to as sums of squares. Okay, so this one is called total sum of squares because it goes across the entire sample. Okay, and it's how much each individual data point varies about the grand mean for the experiment. Okay, so all this blank means I'm going to be writing out a bit. Okay, so we write this. I'm going to start my equal sign back over here because since I write a little bit bigger. Okay, if we expand this out and we keep our indexing across I and j, so if I just, this is rather than write out I equals 1 to t and j equals 1 to ni, this means the same thing here, just a shorthand. Okay, what I'm going to do is take this yij here, and I'm subtracting the y dot dot bar. That's what I have in the first part. So if I come back in here and I say minus yi dot bar plus yi dot bar, I've not changed the value of that expression any. Agreed? That's the same thing I subtracted, I added right back. Well, the reason I do that is because when I square things, I want to keep these two things together and those two together. So whenever I square things with for a given value of I and a given value of j, square the first term, square the last term, we have that cross product term in the middle. So what does that look like? So this is equal to sum across I and j of this first term, yij minus yi dot bar, quantity squared, so that's squaring this one, and then pulling this summation across, plus 2 times the sum across I and j, the expressions yij minus yi dot bar times the quantity yi dot bar minus y dot dot bar, quantity squared, no squared, plus this last term squared, so plus the sum across I and j of yi dot bar minus y dot dot bar, that quantity squared. There we go. Well, what happens in here, this first term does not simplify because it depends on j, so every term changes along in there. The second term, however, won't give you the details for it, but luckily for us, it goes to 0. And the reason it does is because when we look here, we know the reason we square these deviations is we know the mean is the algebraic center of all the data. So if I didn't square the means like this, those would sum up to 0. Okay, and so that's what's going on over here. It's the short story. This last one, as j changes, this term inside that we're adding up doesn't change. We're adding up the same thing in I times, right? And so that last term goes to sum of the ni's times the yi dot bars minus y dot dot bar quantity squared. Doesn't depend on j. So when I look at this one, this measures how much each observation varies about its sample mean, or how much random error variability there is in each of those groups. And so this first one is referred to as the sum of squares, right? It's the sum of squared items. Due to error, or within each group. The second one, we're looking at how much each group varies about the grand mean for the experiment. So how much what is the sum of squares due to group differences, and the term we use is treatment rather than group. Shorthand for treatment is TRT. All right, and so that this will be sum of squares error plus sum of squares treatment. Now you may have been familiar with this in the previous course where this was referred to as sum of squares within and sum of squares between. Okay, so we want to modify that. I don't care for that as much as this because we tend to use the error and the treatment variation terminology a little more broadly used, I guess. All right, I write total sum of squares. I think our author may write SSTOT, which looks a lot like SSTRT. So I tend to write total sum of squares equal to the error sum of squares and the treatment sum plus the treatment sums of squares. This total variation or total sum of squares, when we started off here, this is a positive piece, isn't it? Because it's these items all being squared, so the smallest that the total sum of squares could be is 0, right? We have broken it up into two pieces that are both the sum of squared items. There's no way I can get a negative out of either of these pieces, right? Sum of squares are always positive. If you come up with something that's negative, you're doing it wrong, okay? Sums of squares are positive pieces. So we have this one larger positive variation divided up into two smaller pieces that attributable to error variability within each group and how do our treatment levels differ from each other. So if the null hypothesis is true, all of our y bars should be close to each other, right? If the null hypothesis is true, then each one of these yi dot bars is trying to estimate the same thing. So they all should be close together. So if the null hypothesis is true, and all those yi dot bars are close together, then this value over here is going to be close to 0. And I'm adding up all these differences that are close to 0. So if the null hypothesis is true, I would expect this sum of squares treatment to be small. And that it's just going to measure what I see due to random variation alone, right? If it is false, at least one of those yi dot bars is different. And if one of those yi dot bars is different, that's going to make one of these, at least one of these pieces, be farther away from 0. And such squared is going to make it larger positive value, and that's going to increase sum of squares treatment, right? So if the null hypothesis is false, this piece is going to tend to be larger than what I would see due to error alone, right? So now then we need to look then at how do we put that in, these sums of squares information together in one place. I'm in an ANOVA table. All right. Anytime you compute a sum of squares, it has degrees of freedom. From today, henceforth, or for the rest of your life. Anytime you measure sum of squares, it has degrees of freedom. Okay? And so that for what application or how do you figure those degrees of freedom is important then for the test that we compute. All right, we take this, though our sums of squares are additive here, we talked about each of those being positive pieces last time. The degrees of freedom are also additive, so the total degrees of freedom associated with the total sum of squares can be broken up into two pieces, that attributable to the error degrees of freedom and the treatment degrees of freedom. For this application, these are grand sample size minus 1. For error, it is the grand sample size minus the number of treatment groups or population means being compared. And then the treatment degrees of freedom is the number of groups minus 1. If we divide each of the sums of squares by their corresponding degrees of freedom, we get a mean square. And those are two variance estimates. We call that mean square treatment and mean square error. So if we're wanting to test the simultaneous equality of these different treatment means versus the alternative that at least one of those is different, we need to compare these two variances. Well, we already said in that text, if those means are all equal to each other, the yi dot bar should be close together and the sums of squares treatment would be small. Well, null hypothesis is true. This mean square treatment is just another measure of error variance. Whenever we take a sum of squares and divide it by its degrees of freedom, then it becomes a variance. Variation is just the sum of squares. Slight difference in English there. Okay? We want to be able to compare these T group means for equality. So we want to be able to look at these two variances. How do we compare variances? F-test, right? One of our review topics from last time, we have an F-test. Well, that's really what that's what we're heading towards here. Okay, the conditions again we're operating under, we'll rewrite our conditions or assumptions. We have T independent random samples. That independence, there's nothing linking these two groups together. That our populations are normal, and that our T variances are all equal to each other, and together we call that this sigma squared with subscript epsilon, some common error variance. That's what the epsilon refers to as error. Okay. The mean square error that we compute up here is an estimate of this sigma squared E. Epsilon, pardon me. The other book I teach this out of uses E, not epsilon. So if the null hypothesis is true, that mean square for treatment on the previous page estimates this error variance. If the alternative hypothesis is true, then the mean square treatment is going to be larger than that we'd see due to error alone, the sigma squared epsilon. So how do we compare the two variances? We said F-test. Specifically, is the variance among treatment means larger than that due to variance? So not a two-sided F-test as we reviewed, but a one-sided F-test. So we construct our F-test. Then as follows, that our F is going to be computed by taking the mean square treatment and dividing by the mean square error. Mean square treatment is always in the numerator. Okay, and so just repeating it here, If you printed yours off, you may have them on the same page if you did a 2-on-1. But we're looking at the simultaneous equality of these T treatment level means versus the alternative that at least one is different. And so that if we have an F test, well, last time we talked about the F distribution, we would reject for values of F that were either small or large. In this case, I want to know, is the mean square among treatment means larger? Not just different, but just specifically larger. So that directional language tells me this is a one-sided test. I'm going to reject the null hypothesis only if what? If F is big and larger than some F determined by a right-hand area of alpha, T minus 1 numerator degrees of freedom, and N dot minus T denominator degrees of freedom. Because this mean square treatment has T minus 1 degrees of freedom in the numerator and has a grand sample size minus T degrees of freedom in the denominator, right? So this will always be a right-sided test. So whenever we draw the F distribution, it's always positive. And what this notation means is that we're looking at this area to the right is our type 1 error level alpha. The shape of this curve changes as the two degrees of freedom measures change. If you had your previous course, the prerequisite course from another textbook or at another university, your notation may have been a little different. So I'll explain the notation I'll use throughout the course. This subscript, the alpha, whenever we put an alpha or a probability in the subscript, that's always right-hand area in this book. Okay? The degrees of freedom, then when you look at an F distribution, numerator degrees of freedom are always listed before denominator degrees of freedom. Always. Now, it could be that the book that you looked at may have put the alpha last or first, or put the alpha as the superscript or something like that, or put all of this in parentheses following F. So the alpha can move around, but the order of the degrees of freedom is always the same. Okay, so we talk about alpha here being right-hand area because some references report left-hand area, so always know what you're looking at. So if they're very large values of probability, and they're probably left side area. Okay? We take all of this information that we've computed, sums of squares and mean squares, and arrange them into an ANOVA table. So all those pieces come together in this way. So this you should have seen before, as hopefully in the prerequisite course. You didn't do a lot with an analysis of variance, but probably just had the barest introduction to it. We have a neat way of arranging then all of our degrees of freedom and sums of squares until we get to the F statistic. And we'll do one by hand. We won't ever wanted to do anything by hand. We can use these formulas for computational formulas. Where the total sums of squares, we'd have to take each individual observation and compare it to the grand mean for the experiment. These formulas are computational formulas down here. The reason for this is you probably have like a sum of squared y's button on your calculator. That when you enter data, so that's what if you do the univariate statistics. We'll go through one of these, but I want to talk about this sum of squares error first. So just suppose if our value of t was equal to 2, the sum of squares error would be equal to, using this bottom line down here, would be sample size 1 minus n times s1 squared plus n2 minus 1 times sample 2 variance squared. I'm not sure what I said over there, but it wasn't variance. Okay, and then divide this by nothing yet because that's sum of squares. Divide it in the next line, sorry. Then the mean square error would be equal to this expression up above over n1 plus n2 minus 2. So this n1 plus n2, if t is equal to 2, this value is equal to the grand sample size, right, n dot, Does this expression look familiar from anything we did last time? In the review material, isn't this S sub p squared? When we look at an analysis of variance, we're operating under that equal variance assumption, and that each of these SI squareds are estimating sigma squared epsilon. So if they're each estimating sigma squared epsilon, does it make sense then to take all of those SI squareds and put them together into one better estimator? That's what we're doing with the MSE. Okay, so whenever we talked about a pooled variance in experimenters 1, we're not doing anything different here. We're just extending that to more than 2 groups. Okay, so this analysis of variance is just an extension of that 2-sample t-test that you've done in the previous course. So in this example, we have 15 1-acre plots that are used to compare the yields of 3 varieties of wheat. Each variety is assigned to 5 randomly selected plots. At harvest time, the yield measured in bushels per acre is measured. During the season, 3 plots were flooded and all wheat was lost from those plots. So we see that we have a sample size here of only 12. So dividing things up here, take your calculator. Part of you take your variety 1, variety 2, variety 3. Okay, if you have some univariate statistics on your calculator for whichever group you're running here, you just enter the numbers in the column, and then you can access the summary statistics. So it will give you the y-bars and likely the SI. Just be attentive to whether you're given standard deviation or variance. And then depending upon the calculator, it may do some more things for you as well. Okay, variety 1, what do you have? Yi dot is your sum of observations, or that variety total. 17 for 3. And so if I take the 117 divided by 3, my sample mean is 39. And this variety 1 variance is
63.
63. Everybody agree? Loudest vote wins. Okay. Variety 2, same questions. What's our total? Our Y2 dot bar, or pardon me, Y2 dot. $255. Y2 dot bar is 1. And the variance, S2 squared.
30.4.
30.5. And finally, variety 3. $180 for 4 observations. Y3 dot bar is 45, and S3 squared 18. Given those pieces of information, if we add up these 3 scores, we can get our Y dot dot, our grand total. Adding up 117, 255, and 180, we have a grand total of, I have 552. Our grand sample size is 12. How many observations did we take? And our grand mean is 46. So using that information, because you have the variances, actually doing the sum of squares error is the shorter way to go. Your textbook tends to prefer that, or or getting that by difference. But to do that, you have to get the total sum of squares, which is we can do right at the very top of the screen. And for only 3 groups on sum of squares treatment, I haven't talked about those too much. This actually is not that form is pretty easy to work with only 3 groups. So using either one of those, we need sum of squares error and sum of squares treatment. So use this one for sum of squares error. Treatment, you can use either. If you really want to do the total sum of squares, what that first one means, that double sum across I and j of the I j squareds right here, and that total sum of squares, that means you're taking every observation, 36 squared plus 33 squared, all the way through this entire table till you get to the 47, 42, the last, all 12 observations. And you're computing all of those. And when I did that, I got 25,970. I'll let you go from there. I can get all of our formulas on the screen at one time. So if you were to have done the total sum of squares, I gave you this piece, but I said you would have to have computed all those, the squaring each of the entries to get that. And that's usually what, why individuals will look at computing sum of squares treatment by either of these methods and then by this first method for sum of squares error. So though we're going to be using the computer through most of this course, we verify a few things using hand calculation. So apart from this example, and I'll reserve the right to do this on exam 1, I may ask you a hand calculation there on the ANOVA table. But otherwise, we will be using the computer to do much of our work. One of the things I would caution you about as you work through homework problems and such, that it be attentive to whether you're giving standard deviation or variance. That's usually the big one right there, because if you're going to compute sum of squares error using this formula, and these were standard deviations, you'd need to square each of these pieces in here. All right, so again, be attentive to what you're given in the text of the problem or what your calculator is giving you. Okay, all right, now take our information, and we need to fill in our ANOVA table. So rather than just treatment, our group that we're talking about in this case is variety. You know it, so specify it. And then we have experimental error. I tend to write that instead of error. And then our total. So for this application, what is our variety degrees of freedom? Well, what is it we're testing?
3.
We're testing the equality of 3 means. And all it takes is for at least one of those to be different. What alpha are we going to conduct our test at? 0.05? Because everyone believes that statisticians have that tattooed on one of their upper arms. Filling in the table then, our degrees of freedom then, we have 3 treatments, so our degrees of freedom is 2. Our experimental error is grand sample size, which was 12, minus the number of treatments, which was 3, so there's 9. The addition of these 2 is our grand sample size minus 1. Filling in the information from the previous page, our variety sums of squares was 276. Experimental error was 302. And when we add those together, we got 578, which also agrees with the calculation at the top of the previous page. Mean squares divide each sum of squares by its corresponding degrees of freedom to get the mean square. So 276 divided by 2 is 138. 302 divided by 9 is 33.5. It's repeating. I usually put 4 decimal places. As I compute things in my calculator, I let it carry everything out, and I just round at the end. Drives people that are fond of significant digits nuts, but that's okay. There is no such thing as a mean square total, so do not compute one. All right, 138 divided by is 35.5556, then is our F statistic. And when I did this, I have 4.1126. Agree with those last 3 entries? Now from our 0.05, what's our rejection region? We're going to reject our null hypothesis if the value of F we calculate is large. Larger than what?
The F critical.
F critical determined by
F of alpha D
0.05,
2,9.
2, and 9.
Yeah.
Go to the F tables in the back of your book. Some of you may have calculators that do it, but most of you won't. F table begins on page 729 and continues over to 738. All right, go to the page for .05. The column headers are the numerator degrees of freedom. The row headers are denominator degrees of freedom. So on the .05 page, go to column 2 and the row for 9 degrees of freedom and read your critical value, and it is 4.26. So our 4.11, does it exceed 4.26? So what do we write for our conclusion? Can we conclude that these means are different?
No.
No, that's what we need to say then. So the mean yield does not differ. Across the 3 varieties of wheat. Whenever you write a conclusion for me, you write a complete sentence in the context of the problem. You cite your alpha at which you conducted your test, the test statistic that you're looking at to come to that conclusion, that is the value you calculate, and the observed significance level or p-value. How you compute the p-value from this F table, you're not going to be able to give me a 4-digit number or even a 2-digit number. You're going to give me an interval, okay, because that's the best your table can do. So we look at our table and we stay in column 2, row 9 of every table and go page to page and find the values between which our F statistic falls. And so kind of I have a little scrap paper up here at the top of the page. We know our 4.26 determined an area to the right of 0.05. Okay, we computed 4.11, we're over here. Okay, so if I go to the 0.1 page, the next one bigger, if it were this side, I'd go smaller. So go to the 0.1 page, go to column 2, row 9. That value is 3.01. That value determines a right-hand area of 0.1. So therefore, we would report our p-value is bigger than 0.05 but smaller than 0.1. Does that make sense? And if we're looking at computer output and it prints a p-value, you don't have to look it up, just report what it is. If we're looking at computer output and it gives us a p-value, I don't need to write a rejection region either. Okay, I'm asking you to do both here in this hand calculation, or if a p-value is not given to you, so that way you come up with things that demonstrate that you understand the logic and the pieces fit together. Okay? Our mean square error estimates this sigma squared epsilon. It is this variance estimate that we use to compute standard errors, that is standard errors of the means and standard errors for the difference between means. Estimated standard error of the ith group mean would be variance divided by sample size, all under the square root. This is the same thing in 5013 when you computed a standard error of the mean. If I don't think about formulas, just what it was in English. I took the variance divided by the appropriate sample size and took the square root of the whole expression, right? Same thing here. What's our best estimate of the variance? The MSE. And so the sample size, then the denominator then, is dependent on the number of observations that go into the value being computed in this subscript, right? If you wanted a confidence interval for a population mean, just like it was in the previous course, think about what we're saying here. It is the estimate of the mean plus or minus a critical t-value times the standard error of the estimate. That didn't change. I don't need to memorize a new formula. It's always the same, right? Standard error of the estimate. The degrees of freedom here, what's the degrees of freedom for this t going to be equal to? This degrees of freedom will always be the degrees of freedom associated with the variance in that standard error calculation. The degrees of freedom here will always be the degrees of freedom associated with the variance in your standard error calculation. So for us, in this application, this degrees of freedom is equal to n dot minus t. If we look at the estimated standard error of the difference between group I and group I prime is how this is read. So I and I prime are two different values associated with the treatment levels or the group levels. And it is this mean square error times the quantity 1 over sample size I plus 1 over sample size I prime. And so the denominator here says what's the standard error of what function. So it's the difference between means given here. So if we want to compute a confidence interval for the difference between the I and the I prime mean for the two populations, it's the difference here. This is parenthesis, not absolute value bars. It's because this could be either positive or negative on the left side here, plus or minus this critical t value that we get from reading the table times the standard error of the estimator. So again, it's the estimator plus or minus critical t times the standard error of the estimator. What's the degrees of freedom? The variance that goes into this standard error, which is still the error degrees of freedom n dot minus t. Now, as we change applications, that expression n dot minus t will change, but that degrees of freedom being associated with the MSE or whatever variance is in there, that'll always stay the same.